what you're looking at because you have the concentration so high. If a procedure says add it dropwise, add it dropwise. If you're trying to synthesize something and it doesn't work, switch gears. Try adding it dropwise. You'll save 2 years of your life. Okay? All right. Enough of story time. Everybody feel comfortable with that? Okay. Let's talk about integrated rate laws. Okay to erase this stuff? That's chemical is actually why I quit being an experimental chemist too. I was trying to move stuff from a set funnel into a little vial, and as I was doing it, I sneezed and poured it all over my hands. This stuff is known to cause ADHD and cause liver problems and kidney problems. So I quit synthesizing stuff after that. All right, integrated rate laws. So those two methods were about instantaneous rates, or rates really early on. If we want to know how something's going to change over a long period of time, we have to consider the integrated rate law. So if we want to know the true rate law, need to consider the change in concentration over time. So what we're going to do is we're going to look at a first order reaction, then we're going to look at a second order reaction. First order reaction. Give me a generic first order reaction. Rate is equal to what? Yeah, what do we want to call, what symbol do we want for our reactant? Sure. Okay. We know that's true. Now, what we have to try and do next is we got to frame this. We said this guy's a reactant, right? What we're assuming here is we have some product A that some reactant A that goes to some product. What's another way we could define the rate? Looking back at last class. Yep. So what we could do is we can set these two equations equal to one another. Okay, we run into a problem here though. Can we integrate yet? No, can't integrate. Why can't we integrate? Yeah, A has got to move over here. We need the T somewhere else, right? So what we're going to do next is move the T over and the A over. We move the A over. What are we going to get? If we move this guy over here. Yep. Times dA I want to move the negative sign and the dt over. Can I integrate now? Yep. What are my integration limits for the left? Yep, the initial concentration of A to what? Yeah, some other time down the road, A sub t. And what about my integration limits for dt? And what's the benefit of having it this way? Does k even matter in this? Yeah, it's constant. I can integrate here. Where am I going to start and go to? Yep, 0 to some time t. This integral, you've done it a million times. What is it? Yep. Minus. Yeah. Oops, I guess I should put concentration brackets. Yeah, I'll put the naught out there. I'm sorry. Okay, and what's that equal to? Yep, negative k t. What would I do to show that a reaction were first order? Or what did you guys do? A line. Yep, because it's pcom, why not? Let's transform this into a line. What's my y? That thing. What's my m? Yep, negative k. What's my t? My x? T. And what's my b? Yeah. This is just a constant, right? Because it's the initial concentration we set up. We plot a line. ln of adsorbance at some time versus t. And if it's linear, that's probably what it is. Let's look at a second order reaction. Am I okay to erase this stuff? Okay, give me a generic second order rate law. Yeah. Is that the only one we could have? What's another one we could have? Yeah. This one's known as a bimolecular reaction. Oops. Which one do you want to investigate first? Okay, you want to look at the bimolecular one first? Oops. Okay, so we're just going to rewrite that over. rate is equal to K, A, B. Here, what we assume is we have the following reaction. A plus B gets us to products. Okay, we're going to need a little bit of trickery to get through this. A at some time t. How could we relate that to the initial concentration of A? Yeah, there's going to be some that reacts, right? Which side is has to be larger? Yeah, the initial. So we're going to subtract some amount off X. What could we say about B at some other time? Yes, it is. Why are those the same? Same stoichiometric coefficient, right? Same order, so we're okay there. Okay. Now, what else would the rate be equal to? Yep, and what else? Yep. We could define this off of any one we wanted to. Let's just go for A for now. Okay, so what we have, yeah, we'll go down here. Negative dA over T, and we're going to plug this stuff in. Here, that's a T, sorry. Okay. If we wanted this to be more universal, is it best to put this in terms of A? What connects A and B to one another? I'm sorry, what was that? They're both reactants? Yeah, but what parameter here connects A and B? It does have to deal with that they're both reactants. Anything that they share, the X. So we could define this in terms of X. Because X is really the only thing changing. Oh, I'm sorry. I see what you're yelling at me about. What should this be? Yep, that should be a naught. Okay. We have enough time. Yeah, we can try to go for it. All right, now we want to slosh things together. How would we modify this? What do we want on the left? What do we want on the right? Yep. So we're going to have 1 over a naught minus x, b naught minus x dx. What's going to be on the other side? Yep, k dt. We're going to integrate these things. Where are we going to go to here? Starting at 0, going up to what value? Where nothing's reacted all the way up to x. And then what about for the time side? Yeah, that integral is easy. This one is not. What you have to do is look up a table of integrals. Oops. Have you guys ever used a table of integrals before? Yeah, okay. So if we want to do it for our system, what's that equal to? Yep. E naught minus A naught ln of 1 over, what is it? A naught minus x minus ln 1 over b naught minus x. Okay. What time are we at? We're done. Okay. Next time we're going to finish up here. We got to get this out of concentrations of A and X, and we got to get them like A naught and B naught, and we got to get them into A and B. And we're going to do that next time. The other thing we will do is we will look at the much easier one of rate is equal to K A squared. There it is significantly easier than doing this portion. Yeah, get through the pain first.